Good morning. I am Sahil, and I would begin by thanking the organizers for giving me the chance to speak. And I'm going to talk about thermalization and hydrodynamics in integrable systems. And this is a work I did with Abhishek and Anupam, who are from ICTS, and Herbert, who is from TU Munich. Uh, yeah, so the first question we can ask ourselves is why study macroscopics of integrable system? And the reason is that when we study any system at a macroscopic level, then universal laws emerge, and these universal laws depend only on the symmetries and the conservation laws. And one of the example of this universal law is the second law of thermodynamics, which says that the entropy always increases, but it increases in such a way that it is constrained by the conservation laws. So conservation laws provide us a mean of classifying systems, classifying the universality classes of systems, and it is necessary to study systems with different number of conservation laws to explore the different type of macroscopic behavior. So I gave the example of the second law of thermodynamics, which says that the entropy is always maximum, but the entropy has to be maximized subject to the constraint imposed by the conservation laws. And so suppose I have a system with conservation laws I1, I2, and so on up till In. Then if I maximize the entropy subject to these conservation laws, then what I get is a Gibbs ensemble if Hamiltonian is the only conservation law. But if there are many conservation laws, like for the case of integrable systems, then I get a generalized Gibbs ensemble. And yeah, so the model which I'm going to study is an integrable model. It is a one-dimensional model of hard rods, uh, and all the rods have equal masses, and the size of each rod is A. So integrable systems are further classified as interacting and non-interacting integrable systems. And one of the example of non-interacting is the point particle gas. And the reason it is non-interacting is that because I can map it to a non-interacting gas by simply exchanging the labels of particle after collision. And these particles in the non-interacting picture are called quasi-particles. However, for the case of hard rods, if I exchange the labels after collision, then the quasi-particles, they do not move in straight line at constant velocity. They have these jumps because of the collision. So this is an interacting integrable system. And because it is an interacting integrable system, it will have dissipation term in its hydrodynamics. And the aim of our work was to see the sign of this dissipation from molecular dynamics and to see whether this dissipation leads to uh, thermalization to the generalized Gibbs ensemble or not. And another aim was to compare the prediction of the generalized hydrodynamics with those of Newtonian dynamics. Yeah, and so the conserved quantities for this hard rod gas has, like, when we are doing thermodynamics, they have to be local and extensive. And the local extensive conserved quantities are nothing but the sum of integer powers of momenta. And once we have the conserved quantities, we can find the single particle phase space distribution in the GGE. And we see that it does not depend on the position. So in GGE, the single particle phase space distribution has to be position independent. And however, we will find that for certain initial condition, it will not be position independent. And the initial condition, sorry. So before going to the initial condition, I want to introduce the Euler scale hydrodynamics. And this is the Euler scale hydrodynamics, and it is similar to the Liouville equation for point particle gas, except that this effective velocity is different, and this comes because of the finite size of the rods, which is A. So if A is 0, the effective velocity is same as the bare velocity, but the finite size renormalizes the bare velocity to give the effective velocity. And yeah, so the initial condition I'm going to take is that all particles in the first half have unit velocity, and in the second half have Gaussian distribution. And I let this evolve on in a simulation, and I compare the prediction of Euler equation with those of molecular dynamics, and we found a good agreement between the two. except at the position of the shocks, where molecular dynamics predicts that the shock has to broaden with time, and we found that the shock broadens with time diffusively, as shown in the scaling collapse. For short times, it broadens diffusively, but for long times, we found that the shock saturates to a width which is of the order of root n, where n is the system size. And this diffusive scaling can be explained from the central limit theorem by using an old mapping between the hard rod gas and the point particle gas. And this is the mapping is given by equation 8. Here n less than xi is the number of particles to the left of xi, and the primed variables are the point particle variables, and these are the hard rod variables. And if you actually do the calculation, you will find that this n is proportional to t before saturation, and then it saturates to order n. So according to central limit theorem, uh, the fluctuations has to go as is square root of the number. So this explains the diffusive scaling. And the second initial condition we took is that all particles are confined in one half of the box and the other half is vacuum, and we let it expand, and we found a good agreement between Euler and GHD for this case. Now we wanted to compare the exact solution of Navier-Stokes with that of molecular dynamics. So we took an initial condition for which we can actually solve the Navier-Stokes exactly. And this initial condition was first introduced by Lebowitz, Perkus, and Saik. And in this initial condition, we have a uniform background of particles in equilibrium, and there is a special rod at the origin with unit velocity. And we solve this, we, we did the molecular dynamics for this, and we found that there is a spreading. And it turns out that for this initial condition, the Navier-Stokes can be solved exactly. And so to solve the Navier-Stokes, what we did is that we did a perturbation theory. So at long times, what happens is that this unit velocity, the density of unit velocity quasi-particle, it spreads and it becomes less and less. So I can do a perturbation theory in this delta rho, and I can linearize my Navier-Stokes term. And after linearizing, what I get is a very simple looking drift diffusion equation, and it predicts a diffusive spreading, and the scaling function is a Gaussian, and we found a good agreement between molecular dynamics and the prediction, the exact solution of the Navier-Stokes. Yeah, so this is my conclusion. So we observed that for some initial condition, we do not see convergence to generalized Gibbs equilibrium, and that central limiting arguments can be used to explain the dissipation. Yeah, so that is all I would like to say. Thank you.
We can have a few questions.
Yeah, hi. I guess I'm confused. If you took, instead of this system, if you took a one-dimensional thermalizing system, let's say, point masses of two different types of point masses or something, those systems thermalize. They are described by fluctuating hydrodynamics. But the dynamic scaling there has an exponent of 3 halves, right?
Yes.
So why does this system escape that? I somehow missed, there must be some crucial thing that I missed in your description. Yes. I know it's a different system. I know you have infinitely many conserved quantities.
Yes.
But so how does that allow you to get around what I would have thought is somehow very generic, that the advective nonlinearity will always give you a 3 halves in these one-dimensional problems?
Yeah, so that is a question like which has riddled many people, and I don't have an answer to that question.
So it is a puzzle.
Yes, yeah, okay. But my speculation is that this fluctuates.
Yeah. Okay. I understand that, but in some, okay, so I'm just still, the point is, it's still true that the conserved velocity advects essentially everything. So somehow, how you escape the effects of that nonlinearity, it's not obvious to me, that's all I'm not questioning the result.
That is for the chaotic system. Here, yeah. I have an integrable systems, and
so I guess that that makes all the difference.
I think this extra conservation laws, they changes the universality class of the system.
Yeah, it really, yeah.
And
Okay.
in that, if I have only 3 conservation laws, then the fluctuation terms, they become relevant. But here the fluctuations are not relevant.
Okay, I guess that's what. Okay,
Yes.
thanks.
Okay. Yeah.
You mentioned that the shock expands till square root n size or
Yeah, after saturation.
after saturation. Can you explain why it stops expanding?
Yeah, and the explanation is this old mapping by Perkus. And so this n, the number of particles to the left of the shock, because the system is finite, it cannot grow indefinitely, because the maximum that it can grow to is n, because that is the total number of particles. So it has to saturate to square root n.